cardiac output equations. Now, if you kind of understood what we were talking about in this previous thing, concepts like preload, afterload, contractility, things like wall tension and wall stress, then this thing right here, I mean, it might be new to you, but it's not going to be incredibly difficult to understand. And if it is, let's just talk through it. So, stroke volume, end diastolic volume minus end systolic volume. This is just saying end diastolic volume when the heart's completely filled, end systolic volume after the heart has pumped out the left ventricle volume. So this is whatever's in the left ventricle before it pumps. This is whatever's in the left ventricle after it pumps. So the stroke volume is that minus that. Theoretically, you would want the end diastolic volume to be very high and the end systolic volume to be very low. If the end systolic volume is very high, you could have a problem with contractility, you could have some outflow obstruction, you could have a whole bunch of things. All right? So there's no real reason to just memorize this equation. It's just, kind of makes sense a little bit in that sense. Ejection fraction. Well, that's not too bad. That's just telling you, well, the stroke volume, what you pumped out, over what was there in the first place. Okay, well, the stroke volume is everything that was there in the first place. Ejection fraction is going to be 1. 1 over 1. Or you could think of it as end diastolic volume minus end systolic volume over end diastolic volume. Okay, sure. Cardiac output. No problem here. What comes out equals the stroke times the heart rate. What are you pumping out? Stroke volume. How many times are you pumping it out? Heart rate. Well, there we go. Remember, diastole is shortened with an increased heart rate. This is because you absolutely want to pump out blood. Right? You don't want to spend your time filling up blood not to pump it out. So you'll preferentially shorten diastole over systole. Pulse pressure. Pretty straightforward. And mean arterial pressure. Yes. Cardiac output times total peripheral resistance. Or, here's actually one of the things that I like thinking of. 2/3 diastolic blood pressure plus 1/3 systolic blood pressure plus equals diastolic blood pressure plus 1/3 of the pulse pressure. You can do the math here and see how these things are related. But I like doing 2/3 diastolic blood pressure plus 1/3 systolic blood pressure. Or you can also just do, for pulse pressure, systole minus diastole. Okay, here's the big thing, the Starling curves. This is going to be the big thing for this page, along with some of these things. But this is stroke volume, ejection fraction, cardiac output, pulse pressure. These things all build on each other, so you can't point to one thing as being more important than anything else. But these Starling curves you're going to keep seeing over and over again. You kind of see it here, and you're going to have questions for sure on your step 1 about, what happens with each of these curves when it moves. So before doing anything nuts and looking at those, let's just take a second and look at these. So you can see on your x and y axis you have preload and you have stroke volume. All right? And you can kind of follow along with what they have here. So let's start with heart failure, HF. Well, if you have heart failure, what's going on? Well, you would have very high preload. Why is that? Well, it's because you're not pumping out any of the blood. And so it kind of just pools and stays there. All right? And you'll see that it's not very high on this y-axis of stroke volume. Okay. So, high preload, low stroke volume. And you can have questions on your exam here with your famous numbers or your famous arrows, right? They say, this thing goes up, this thing goes down, one of these things stays the same. So just kind of remember that for a heart failure, you would have very low cardiac output, low stroke volume. They would kind of mirror each other in that sense. But the preload would be elevated. However, with digoxin, which we saw caused an increase in intracellular calcium, you would have kind of an increase here in your contractility. And, oh, yeah, look at this. Boom. All right, and with exercise, your heart rate ends up getting increased. And this is something that I should have covered earlier on. Heart rate and stroke volume in the early stages of exercise, but towards the end, you can't really increase stroke volume anymore, right? Like your heart can't get any bigger. You can't pump out more than what you already have. And so heart rate is what ends up causing the increased cardiac output, not an increase in like your heart size or not an increase in stroke volume. All right, so this should make sense now. With exercise, increased contractility to a certain extent. And you would have, look at all this stuff. You would also have a kind of a decrease, you could say, in your preload, because when you have a whole bunch of exercise, diastole shortens compared to systole. So that's why you have this thing decreasing as you have stroke volume or with exercise.